Next, we'll hear from Howe Industries.
Water. We owe quite a lot to it. It's essential for life on Earth. It keeps us cool on a hot day, waters crops for food, and at one point in time drove the largest industrial revolution the world has ever seen. Mills, factories, trains, all powered by steam, have propelled humans into the 21st century. But our modern technologies have made steam power obsolete, leaving old technologies forgotten in time. Now humans are on the cusp of a new revolution, this time in space. Small satellites by the hundreds and even thousands will be launched, gathering data and connecting our world in ways that were previously unimaginable. In order to expand this revolution further and truly realize the potential of these satellites, we have brought back an old friend, steam. Combined with decades of technology, advancement, and modern insight, steam is being brought to space in a way never seen before. While a satellite seems complex, its basic needs are rather simple. Chief among them is the need to move around in space with a propulsion system. Without this, they face a bunch of different issues. Satellites will naturally decay as they interact with the upper atmosphere, hurling themselves all the way back down to Earth. If you're spending hundreds of thousands, if not millions of dollars on your satellite, you're going to want your investment to last. If you're like most satellites these days, you're probably pretty small, which means you're rarely going to get your way during launch. You usually get dumped out into space with all these bigger guys that chose where to go because they paid the extra money. And if you have high hopes and dreams of going to Mars or the Moon, better luck next time. That's where ThermaSat comes in. ThermaSat is a solar thermal propulsion system, meaning that it gets all its energy from the sun, and it stores this energy on a thermal capacitor, which works just like a regular capacitor, but this time storing their energy as heat. If we take water and we introduce it to that capacitor, it instantly vaporizes into steam, and if we can channel that steam into a nozzle, we get thrust, and thrust is movement. But why solar thermal propulsion with all these other systems available? Well, for starters, our system does not require electrical power conversion. We take the energy of the sun and place it directly into our thermal capacitor. The hotter we can get this capacitor, the more efficient our propulsion system becomes. Our first systems are planning to use water as a propellant, which is safe, non-toxic, and inert. I can drink water, but I can't drink hydrogen that powers other systems. But we all know the real reason why someone would want to use a propulsion system in a spacecraft. Space is expensive, and building a single satellite, let alone a constellation of satellites, is going to add up. Satellites are naturally going to deorbit in a few years, depending on their altitude. These deorbiting satellites cost a lot of money. Take this Earth observation CubeSat, for example. It's 6U, which costs about $300,000 to send into orbit, not counting the cost of actually building and the labor involved with making that satellite. Now that's pretty pricey. But if your satellite keeps dropping out of the sky every 3 to 5 years, you're going to need to replace that over and over. This is where ThermaSat comes in. ThermaSat can keep your satellite in orbit longer by boosting your orbit over time to prevent yourself from burning up in the atmosphere. With a little more upfront cost, you can drastically reduce your replacement costs and increase the net throughput of data from that satellite. ThermaSat enables you to move around in space and explore and commercialize areas that were previously thought impossible to reach. Let's say you want to provide better image or lower latency for your customers. One method to do that is to spend thousands and thousands, if not millions of dollars on research and development to develop a new communication system or a new camera with a better resolution. Another method is to simply lower your orbit. By lowering your orbit, you are able to increase your spatial resolution without actually changing the payload you have. ThermaSat can keep you alive at these altitudes, matching the lifetime you had at your previous orbit, while simultaneously increasing the product you're bringing to your customer. Our baseline ThermaSat unit is designed to fit with CubeSats and small satellites to accomplish this task, but our technologies don't stop here. We are developing ThermaSat 100, a spacecraft designed to operate at extremely low Earth orbits. This region of space typically goes unexplored as it's difficult to get to, but there's lots of science and lots of commercial opportunities in this area. The drag is high enough in these orbits that a typical CubeSat will deorbit in a few months, weeks, or even a few hours depending on what altitude they're at. But why do you care about winning this orbital limbo contest? Being low, as we said, gets you better spatial resolution and lower latency communications, but there's also other huge implications that people can take advantage of. With your orbit being lower, you're going to be moving faster than the satellites above you, so your revisits times can actually decrease significantly based on your altitude. Other payloads, such as radiometric observations, see a vast improvement with being closer to the ground. They require less sensitive equipment that would be required in LEO because of all the extra altitude between you and the ground. Geopositional accuracy also improves because if you're physically close closer distance to the surface of the Earth. Your satellite and payload will suffer less radiation effects because of your closer distance to the Earth. Any orbital debris in this area is going to quickly deorbit because of the increased drag, a problem that's going to occur in low Earth orbit with the thousands, if not tens of thousands of satellites that are going to be launched. This region also encompasses the ionosphere, a rarely studied region of space that actually greatly affects communications for NASA as well as the military. Thermosat 100 has been specifically designed to meet the requirements of this challenging environment. By including your payload in Thermosat 100, you're able to bring the same, if not better, services at a cheaper price to your customers. But what about those who want to break free of the bonds of Earth? Those that want to explore to the Moon or even Mars? Thermosat Plus is the answer. To address larger satellites and a growing cislunar economy, Thermosat Plus has been specifically designed to transport cargo and last-mile services to the Moon and beyond. This system takes solar thermal propulsion to a whole new level. Utilizing hydrogen as a propellant, Thermosat can achieve extremely high specific impulse and thrust values, typically only seen with nuclear thermal rockets. This is all without the adverse effects of having to deal with nuclear materials and launching them into space. Thermosat Plus offers tug services in Earth orbit, geo, cislunar space, and eventually all the way to Mars. With unparalleled efficiency and thrust, Thermosat Plus will truly open the cislunar economy and beyond. While this is the future we envision here at Thermosat, we need to take incremental steps. Our baseline system will be debuting in 2023, featuring a system that will fit into 6U and larger, as well as 3U or larger satellites. Thermosat 100 will be introduced in late 2024, with Thermosat Plus shortly following in early 2025. Sales as well as investor funds will help finance the research and development for these two larger systems. In this figure, you can see how other systems compare to each other when we consider their power consumption and thrust levels. On the left-hand side, you have electric propulsion systems, which, while extremely efficient, produce only a small amount of thrust, requiring lengthy time frames to deliver payloads to specific orbits. On the right-hand side are systems that produce a large amount of thrust, such as chemical systems. These systems are fast and maneuverable, a considerable advantage in crowding orbits and a rapid deployment of constellations. The Thermosat baseline unit requires only a small amount of power from the spacecraft, getting most of its energy for thrust from the sun. Combined with water as its propellant, it can produce thrusts on par with other high-thrust monopropellant and bipropellant systems typically classified for CubeSats and small satellites. Thermosat Plus sits in the upper right-hand corner of this chart with extremely high specific impulse compared to other high-thrust chemical systems. This enables an extremely efficient and maneuverable thruster for in-space transportation. Our projections place our minimum viable product addressable market at just over $72 million. The Thermosat baseline unit will act as a stepping stone for our other technologies that have the potential to really disrupt the current industry. Thermosat Plus in particular will address the last-mile services and in-space transportation that is quickly growing. With high thrust and specific impulse, Thermosat Plus can only be matched by another solar thermal system or a nuclear thermal option. The expected market potential in this area is expected to quickly increase to over $10 billion in 2030. With increased interest in cislunar activities, we believe this market will grow even further. The team is led by Dr. Troy Howe, the founder of our parent organization, Howe Industries. He has expertise in nuclear power and propulsion systems. And while we have taken the nuclear power out of Thermosat and replaced it with solar thermal, his expertise in this area will lead Thermosat to success. Our CTO, Jack Miller, was the lead engineer for the Thermosat Phase 1 SBIR with the National Science Foundation. He led the development efforts for this propulsion system, as well as led the team the National Science Foundation's I-Core program. Our managing director, Marvin Weinberger, is a serial entrepreneur and inventor. He has led many successful companies to great success, and his guidance with Thermosat leads us to a promising future. Thermosat has been funded by a National Science Foundation Phase 1 SBIR grant in 2019 and 2020. We are eagerly awaiting a Phase 2 proposal. We've also been subcontractors on several Air Force SBIRs, with companies leveraging our technologies to increase the access to space and the cislunar environment. In the coming months, we will spin off Thermosat from Howe Industries, its parent organization, and retain an investment banker for a Series A. We are currently seeking $5 million in Series A funding. We will use these funds to develop Thermosat and make it into a product that is truly commercial off the shelf and readily available. This funding will also go towards the research and development of Thermosat 100 and the Thermosat Plus propulsion system. Funding will also be used to expand our team, bringing valuable talent to the success of Thermosat. Steam has powered an industrial revolution in the past, and now it's time to bring that technology back to drive our own revolution in space, powered by Thermosat.
All right, thank you, Thermosat. So do we have any questions? Greg, if you want to go ahead and start off.
Sure. Thanks, Robert. Great presentation there. When you said 203 seconds, I went, yeah, sounds about right. When you said 836 seconds, my eyebrows kind of go up through my top of my head. How I don't even know and I understand how that is possible.
So that system uses hydrogen as the propulsion system, as a propellant. So you can reach much higher specific impulses because of the lower molecular mass. And we're heating that system to over, I think it's over 2,300 degrees Kelvin. So it's a much higher temperature, lower mass or lower molecular mass system.
So you basically you've got the equivalent there of a nuclear thermal system, but what you're doing is you're using your capacitor to heat hydrogen.
Exactly.
Okay, I got it. Do you see a scalable business in this? I mean, I know you've put up like 72 million bucks, but I mean, is this something that you're looking at for small thrusters for a lot of CubeSats, and that's how you grow it up to bigger units, or is this something that you see as a cislunar transportation system?
So it's definitely growing it from the small thrusters for spacecraft, something on the 6U, 12U size. We also have a 3U version, our system that would be compatible with 3U, and growing it to much larger cislunar and hopefully even Mars transportation with the ThermaSat Plus system, because it's considerably larger and it's much greater efficiency.
I'm sorry, last question. Presumably this could only work within the inner solar system, is that correct?
Right. Its best use case is going to be around Earth and below because of the decreasing solar flux as you go out. But that basically just means we'd have to increase the size of our reflector if we wanted to. So we could make that work as well, but best use case is going to be around the inner solar system.
Okay, thank you.
All right, Bruce.
Yes. Just a quick question, and this is kind of obvious, I think, but a lot of the smaller spacecraft, because they are small, they have a very difficult time dealing with thermal loads. And I think I heard you say 2,000 degrees, or I'm not sure if that's the water system as well. But it seems like you're really going to be working hard to manage that. How do you manage that kind of a heat load on a very small spacecraft platform?
So you are correct. The 2,300 Kelvin system is the larger system. So that won't be on the small satellites. The smaller ones have a capacitor temperature. I can't remember the exact number right now. It's over 1,000 degrees Kelvin. But we have a unique optical system that prevents that radiative heat from reaching the spacecraft. And we're also planning on using some 3D printed ceramic structures to try to isolate that thermal capacitor as much as we can. And that's what testing in the phase 2 will reveal, if we have that'll show that we have the ability to keep that system isolated from the rest of the spacecraft to make sure we're not heating it up. That's a big concern of ours. So we're keeping track of it though, but it should be isolated from the rest of the spacecraft.
All right, thank you.
All right, John Dankenich.
Yeah, thanks for the presentation. So what would you say are the key performance differentiators between your technology and some of the other water-based solutions, such as Hydrus or perhaps more relevant, Momentus?
Right. So Momentus has I believe it's a microwave system that heats the water, and that's electric. So that system, obviously, one of the disadvantages of it is that it requires so much electrical power input. And the benefit of their system is that they get really high ISP but low thrust. Our system requires virtually, very minimal power input from the spacecraft. We have a couple solar panels on the side to help mitigate the issues with pointing, but we require a significantly smaller amount of power, and we still get relatively high thrust out of it that's comparable to these, monopropellant and green propellant systems. So it's really the low power input that differentiates us from these other systems.
All right, thank you. Chandra.
Hi, great presentation. So this isn't my area of expertise, so I apologize if these are not great questions and I'm using up your time. I'll ask them quickly. Is there a drop off of propulsion output as the fuel level depletes? And is freezing and expansion of the water a potential issue for breaching contaminants?
Right. So we are aware of like potential freezing issues with the capacitor, or not with the capacitor, with the water. As I mentioned earlier, we're probably going to be concerned more with preventing heat from leaking into the spacecraft. So I don't think we'll have that issue, but we'll keep track of it, make sure none of the water freezes in our propellant lines. We might have to have some electrical power input to prevent that from freezing, just keeping the water at 0 degrees Celsius to make sure nothing freezes there. To answer the first part of your question, we have spec'd the system out to maintain the same level of performance, like 1 Newton all the way through to its end of its useful lifetime. So it would degrade after that because you're going to lose pressure and stuff like that. So we've spec'd it out. Our spec sheet says that this is however X amount of meters per second for the useful lifetime of the propulsion system.
Mm.
So it does degrade after that. It'll have a burn curve, I suppose, after the completion.
Okay, thank you.
All right. Zach.
Hi. Quick question, and maybe you addressed this and I missed it, but could you explain some of the business model for me? Because I'm trying to understand whether or not your system, particularly the Thermosat, gets retrofitted into existing satellite systems, or if you are offering an all-in-one system that would replace other satellite systems to various companies.
Right. Yeah. So our first product would be the Thermosat baseline unit, which was that kind of square-shaped propulsion system you saw. That would fit into other spacecraft, so like a 6U or 12U spacecraft, and we would sell that as an individual propulsion system. As time goes on with Thermosat 100 and Thermosat Plus, those systems would be all in one. We would provide the spacecraft bus as well as the propulsion system, and you would simply insert your payload into the Thermosat 100, and you'll be able to fly around in very low orbit. Thermosat Plus, that one is obviously a complete propulsion system, and it should be able to transport you to and from the moon. If Marvin or Troy want to chime in on that, I think I described it as we envisioned, but let me know.
I think you covered everything from my end.
Okay, that clears it up. I wasn't. It's obvious the latter models were all encompassing, but I was unsure as to whether or not the first model was or not. Okay.
Right, and that's a design choice because our team, we want to gather the experience of that propulsion manufacturing and getting things into orbit first.
Right. Okay. Thank you.
All right, Greg, do you have a question?
Yes, I do. Sorry, the mute button. Very interesting. Very interesting technology. I guess I was thinking of, what you're envisioned for the planned operational life, how long you could maintain your system without having to fire it. Because I was thinking it may be potentially kind of a backup booster system, not the primary propulsion system for a satellite to help it, maintain its length longer, as you were saying in your demo. So how long could you keep it indefinitely? What are you planning to do that for your operational design?
Right. So I don't know if we have I can't really think of a design lifetime right now that we have in mind. That'll be revealed in testing of our phase 2 to see how much the nozzle degrades with firing the thruster, and if any sort of adverse effects come from heating the thermal capacitor and that cyclic loading of it, the thermal load with that. So I don't think we have a design lifetime at the moment, but we have thought about the option you talked about, where it's essentially a backup system that occasionally boosts up the satellite. And we designed it in such a way to prevent it from hindering the primary mission of the satellite. So with nadir pointing, we didn't want to have to constantly be pointing towards the sun and prevent you from doing your mission. So that's why we included these solar panels on the body, so that it can heat it up while it's not pointing towards the sun directly, and then heat up from the sun when the capacitor turns towards it. So it should not significantly affect the spacecraft and its its operations. But we'll investigate the mission lifetime in the phase 2 after we get some more data.
Thank you.
Do we have any other questions? All right, well, thank you very much.